Okay, so now we have question 6. Now, first of all, we know that from the lecture that if a function of dimension of n is convex, then from any line and any point, like from any direction, from any point, if you draw a line which makes a one-dimensional function, if you can prove all of them are convex, then the original function is convex. So we'll just focus on proving the second part. So first of all, in question 1, we already proved that when alpha is 0, which means at the starting point of x, like around x, this point, that this is the Hessian of this point. And this is always bigger than 0 because the Hessian is positive definite in this case. So for any line, its starting point, the Hessian is always it's always going to be positive. But now we want to deal with the whole line. We want to prove that the whole line is convex. So we need to prove that also in the case of when alpha is not equal to 0. But this is also very easy to see, because if you look at one line, you can define this line at any place. So let's say we let's draw it like this. So if you have a line which is like this, whatever, so you can simply start on the function, on the original function at this point or at this point. Your function is just going to be a shift, but like the value is the same. So for example, if you look at, let's say if this is the 0 point, let's draw it again. So let's say if this is the 0 point of the line that starts over here, then we can simply define another line that the 0 starts from here. And the only difference is the x is different. So you pick a different x along this axis, along the r and whatever it is. So simply we define a new like we just define a new x in this point, which is the shifted version. So in this case, that the value, the second derivative from at the origin, when alpha is 0, it's the same as when you look at this function at this point.